Hello, my name is Ethan Jeon, and today I will be talking about my review paper on the pigeonhole principle. This is not the full paper, but this is rather just a concise presentation on the principle as a whole with a few examples. Here is the principle. If n number of items are put into m number of containers, with n being greater than m, then at least one container must contain more than one item. For example, as the diagram shows, if there are 10 pigeons in 9 containers, we can guarantee that at least one container will have to contain more than one pigeon. This logically makes sense, as even if each container holds one pigeon each, that would still leave one pigeon left, forcing it to be in one of the containers. This causes at least one container to hold 2 or more pigeons. One common example regarding the pigeonhole principle is the sock drawing example. For example, if there are 20 black socks, 30 red socks, 40 blue socks, and 50 gray socks in a sock drawer, what is the least number of socks to be randomly drawn in order to guarantee that there will be at least one matching pair? To solve this, we can think of the socks as pigeons and colors as pigeonholes. Since there are 4 colors, we can conclude that there has to be more than 4 socks drawn to ensure a matching pair, which is 2 socks of the same color. The number of socks drawn, therefore, has to be more than 4, but as small as possible, so the answer will be 5 socks drawn. One not so common example regarding the pigeonhole principle is the equilateral triangle example. Here is the question. An equilateral triangle has side lengths of 1 cm. Show that for any configuration of 5 points, on the side or in the interior, that there is at least one pair from these 5 points such that the distance between the 2 points in the pair is less than or equal to 0.5 cm. This is a much more difficult problem, and to solve this, we can divide the equilateral triangle into 4 smaller ones to help us. As in the diagram on the right, we have divided the triangle into 4 smaller ones, each with side lengths of 0.5 centimeters. We can think of the sections or smaller triangles as pigeonholes, and the points as pigeons. There has to be 5 points that are placed across 4 sections, and applying the pigeonhole principle, this leads us to the conclusion that at least one section will contain at least 2 points. Within the smaller triangle with 2 points, the maximum distance is the side length, which is 0.5 centimeters. Using a diagram combined with the pigeonhole principle, we have now proved the statement from the original question. In conclusion, there are some key takeaways from the pigeonhole principle in this presentation. First, the pigeonhole principle might seem like it is a fairly easy concept to understand at face value, but it becomes a lot more challenging when it is asked to be applied to more complicated problems and situations. Next, the pigeonhole principle can be applied into real life in many ways, and it makes finding solutions to problems in the real world a lot more simple and easy to understand. Finally, this presentation was an extremely simple and condensed version of my full review paper, and the explanations even for the example questions above in the presentations were not thorough or perfect in the slightest. However, all of these things and a lot more will be fully captured and put in my final review paper that I will submit at a later date. Thank you for listening to this brief presentation about the pigeonhole principle in my review paper, and I look forward to continue working with these topics as I enter my high school years.